arises from this first problem is how are we going to be able to express the relationships between the different types of the ontology themselves? And the way that we're going to address both of these problems is to represent all of our nodes and edges as low-dimensional embeddings. So to get an idea of what this means intuitively is that we want the representations of semantically similar types to be encoded as spatially similar vectors. So if all our node vectors were two-dimensional and we were to plot them, we'd wind up with disease types in one area of the space, things like drugs and chemicals in another cluster, and so on and so forth. And the same concept can apply to our edge vectors as well, where again, the spatial relationships are going to correspond to semantic relationships. So far we've been talking about the biomedical domain, but these methods are actually applicable to most any domain. And for ease of sort of intuitive understanding, we're going to transition to the more general domain of people and places and organizations. So again, we're talking about knowledge graphs where nodes are concepts and entities, and the edges are relationships between them. So how do we actually get a knowledge graph? So in reality, these graphs are typically filled with hand-curated facts within a fixed, predefined schema of node and edge types. And this hand curation inevitably is going to lead to a high amount of incompleteness, as it's not actually feasible to enumerate and write down all of the possible facts. So what we really like is a way of automatically building these graphs. So the goal of automatic knowledge-based construction, or AKBC, is just that. We want to go from a corpus of unstructured text to a knowledge graph of entities and their relationships. So to actually accomplish this takes a few steps. So first, we're going to find all of the mentions in our documents of entities and concepts that we're interested in. So in this example, people, places, organizations. And next, we're going to link together mentions that are referring to the same entity. So here there are 4 mentions, and they're all referring to a single entity, which is Bill Gates. And we could do this over our whole corpus and collect all of the entities we found, as well as all the co-occurring pairs of entities. And often we aren't going to be starting from scratch, but instead we can often have some initial, incomplete, human-curated knowledge base. So we can consider the structure schema defined in those knowledge bases as a starting point, which will define some of the types of the entities and also of the entity pair relationships. And as we talked about earlier, the schema is actually going to suffer from the same type of incompleteness as the knowledge graph itself. So some human pre-decided what are the set of possible types that would define all of the semantics that we would ever want to consider. And again, this is inevitably not going to be able to cover everything. But if we look at the text itself directly, we can instead find textual types that express kind of a limitless amount of very fine-grained semantics. And jointly considering these structured and unstructured types together is what we call universal schema. So next I'm going to talk a bit more about the work I did on universal schema. So for now, let's just look at the entity pair relation matrix. So here the rows represent pairs of entities, and the columns represent relationships between those entities. So at this point, we have this massive binary co-occurrence matrix of the observations we've made. So here, a green cell depicts a fact observed in our training data. But ultimately, what we want to do is be able to predict new relationships that we never directly observed. And so how are we going to do that? And one way is to factorize this matrix and learn an embedding for each row and each column. So to start with, all these vectors would be randomly initialized, but we can then learn the parameters of the model, for example, using a ranking loss. So we could select a positive cell that we observed in our training data, and then randomly sample an unobserved cell to treat as a negative example. And the score of each of these cells is just going to be the dot product between the corresponding row and column vector. And the objective is then simply to make the score of the positive cell higher than the score of the negative cell. And to think about this intuitively, what's happening here is we're updating the values of the vectors such that positive training pairs are being pushed closer together and negative pairs are being pushed farther apart. And throughout the course of training over the full corpus, we just want to find what is the best possible setting of these parameters such that overall the positive things are closer together, negative things are farther apart. So after training our model, we can use these learned vector representations to score the unobserved cells in our matrix. And in that way, we can infer new relationships between these pairs of entities. So this is the model from the original universal schema paper, but unfortunately, in its original form, it has a couple shortcomings. So the first is that there's no sharing of information between very similar types. So for example, even something like born in and born in the city would be represented as completely disjoint column vectors in this model. And there wouldn't be any sharing of information between them. And the other issue is that the model is unable to make predictions about types that it didn't explicitly see during training time. So what that means is if we have a new document containing a new sentence, we don't have any learned vector representation for that column, and we won't be able to make new predictions about what it means. What is the meaning of that text? So to address this, we are going to replace our explicit column parameterizations with some learned neural text encoder. It's going to map arbitrary text into a vector that exists in the same embedding space as our existing column vectors. Now we can use that to make new predictions. So the way that we can think of this is that we have some function that just takes in a piece of text as input, and it's going to output a single vector encoding the semantics of that piece of text. So we'll talk about a few different neural encoders in this talk, but the main point is this takeaway message here. So for concreteness in this initial model, the first thing we do is to map words to these vector representations. So these word embeddings have the same properties as the embeddings we talked about previously, where spatial similarities are going to correspond to semantic similarities. And because these word embeddings are context independent, we're going to pass them through a neural network that contextually encodes them. So here, the network is a type of recurrent neural network. And the main point is that the output of this LSTM, each of the outputs is going to correspond to each of the input words. But now these representations encode not just information about the word itself, but about the way the word is used in the sentence. And finally, we can get a single vector representation for the entire sentence from an operation like a max pool. So here, each of the k dimensions of our vectors, the output of that dimension will be the maximum value of the inputs for the corresponding dimension. Okay, so one really interesting property about this model is that we can actually map any language into the same embedding space. So we could have some columns in English, some in Spanish, some in Russian, and so on and so forth. And because there will be some shared entities across these languages, the different embedding spaces will become aligned. So a little more concretely, if in this example we see that Melinda and Bill Gates are entities that exist in all three languages, when we train the model in the way we talked about before, the English columns are going to be trained to be more similar to the Melinda and Bill row vector, as will the Spanish column and the Russian column. So all of these different languages are being pushed towards the same target, and in that way they're aligned and anchored by these shared entities. And through this translative learning, we showed we could even perform zero-shot relation extraction in Spanish using only annotations in English. So we ran a very large model and some follow-up work on about a dozen languages and found some interesting outputs to look at. So on the left here, we have an input from a non-English language, and on the right, we can see some of the similar English patterns that the model returned. So we'll see things like capital of in Spanish being mapped correctly to capital of in English, was elected president being similar to re-elect, love eating being similar to munch, and so on and so forth. And we also use this model as the basis for our system in this DARPA attack KBP competition, where the setting for this shared task was given a corpus, construct a knowledge base. So this is exactly the full AKBC setup. And our system was ranked first in the 2016 multilingual KBP competition and also the top system on this Stanford KBP leaderboard. Right. So next, let's look back at our entity type matrix. So now in this matrix, the rows are individual entities and the columns are types that types for those entities. So things like person and location and politician. And so far we've been treating these column types as a flat set, but in reality these types exist in a rich hypernym hierarchy. And we'd like to be able to leverage that additional structure to improve our models further. So just as before, each of our types can be represented by a single vector. But now we're going to enforce an additional constraint on our embedding space to respect this type hierarchy. And one way we can do this is with a scoring function with a bilinear operator which produces an asymmetric score. And this is important because the hierarchy is asymmetric. And we'll end up training our model such that we maximize the scores for edges that exist in the hierarchy and minimize it for the edges that don't exist. We additionally ran some experiments with a similar model, which instead uses a complex bilinear function. In this setup, types have both a real and imaginary vector, and the score of a hyperimage is this Hermitian dot product between those types. But the main takeaway is the same thing, where we have some scoring function that can tell us how likely is this edge to actually exist in our hierarchy. So what we'd really like to do is, given some new sentence, we want to map that sentence to a vector whose representation will fall in the appropriate spot in the hierarchy. So here, Melinda Gates should be represented as a founder and a person, and her foundation should be a nonprofit organization. And in this setup, we'll score these sentence type pairs with the same function that we use to score edges in our hierarchy. And in that way, we're actually putting the text in the same hierarchy. Okay, so we can look at some results, and these first results are on this data set Figer, which is kind of the most widely used data set for this task, which is fine-grained entity type prediction. So we can first see that our base model, which is a convolutional neural network, is comparable to the previous state-of-the-art without using any handcrafted features or external resources. And most interestingly, we see that our type-aware hierarchy training actually improves the results quite substantially, and our best model is even comparable to a much more complex model, which did use external resources and additional features. And what's most interesting about this is that the particular data set actually has a fairly small hierarchy. It has only 121 types and only a depth of 2. Yet we were still able to get benefit from modeling these hypernym relationships. So we wanted to see how can our models take advantage of even bigger hierarchies. And to do this, we created this new type set, which we called TypeNet. So it has about 2,000 types and a maximum depth of 14 in the hierarchy. So we can just see some examples of the structure of TypeNet. We'll see very fine-grained types like Olympic host city, different foods, different subcategories of athletes. And the way we're going to evaluate TypeNet is a bit different. So in this case, we don't actually have a direct labeling from individual sentences to individual types. Instead, we only know that this sentence contains Melinda Gates, and that we can describe Melinda Gates with a set of types. So now the problem is instead to map a set of sentences or entity mentions that contain Melinda Gates to the set of types that we know her to have. And we can think of this as entity-level type prediction as opposed to mention-level type prediction, which is when we're explicitly labeling each sentence. So the way that we can do this is we can first map each sentence to a single vector. So our neural encoder here is a CNN. And then we could score each sentence against each of the types in our whole type set. So I'm only showing the positive types here, but in reality, we'd score it amongst all 2,000 types in the type set. And this will give us our mention level scores for these 3 mentions. And then we can aggregate these all together using some pooling function, and this will give us a single set of predictions, which are our entity level scores. So these are our predictions about the entity Melinda Gates rather than any of the individual sentences. And what we find is that using our hierarchy actually substantially improves our results in this case. So our best model actually gained over 10 F1 points over the equivalent model that treated the types as a flat set. So this is evidence for the benefits of this hierarchical training. So we're also really interested in using these same types of methods for other domains. Particularly, we're interested in this biomedical domain. And to help us do that, we first wanted to create a rich data set of text annotated with biomedical entities. So here's an example of 2 titles and abstracts from biomedical research papers. And then we then got expert annotators to identify things like genes, diseases, pharmacological substances, biological functions, proteins, as well as several other types. And additionally, in addition to identifying these mentions in text, we then had them link them to the specific entity in a knowledge base, in this case, the UMLS knowledge base. And this is particularly nice because UMLS arranges their entities in a very rich hierarchy. So this data set is about an order of magnitude larger than some of the previous comparable data sets, and is a good resource if this is a type of research you're interested in. So on this data set, we ran an entity linking experiment. So what that is mapping those mentions to the correct entity in the knowledge base. And we first see that all of our methods are outperforming this baseline string-based method, which is actually quite a strong baseline in this setting. And most interestingly, we again see that modeling the hierarchy is able to improve our results. Though they're not quite as substantial as the previous results, we still see a benefit from modeling the hierarchy. Okay, so we've been talking a lot about knowledge graphs, which we can use to encode information about entities. And one property of these graphs that can actually be a bit detrimental is the fact that they encode knowledge at an abstract level. And what I mean by that is that the information is not necessarily grounded in any particular instance or piece of data, but instead we're encoding some global notion about the entities. And because we're doing this, we can end up in a situation where the graph can actually contain seemingly contradictory information, such as a chemical being both a treatment and a cause of a particular disease. And when you go and look at the specific instances of these entities, you can see, for example, that in one paper they found that the drug did treat the disease. And in a second paper, they said that the drug actually can cause the same disease. And importantly, it's not even the case that one of these papers has to be wrong. In the end, both facts are actually true, but in different contexts. So I think the notion of how we can represent knowledge in context is going to be extremely important for advancing knowledge representation reasoning research going forward. So I'm going to talk a bit about a few initial steps in this direction before I go on to talk about how we can take these ideas even further in the future. So in our model, our abstract entity representation is a single vector, right? So, but an alternative approach that would allow us to capture the context that an entity can appear in is to instead consider the individual instances themselves, which in this case is the types of the entity. So instead of representing an entity as a single vector, which is an abstract and general notion of that entity, we can represent them as some function over the known specific types for that entity. So I'm going to talk a bit about the work we did looking into this a bit. So we looked at a few different methods for actually aggregating these types. And the first are query-independent methods. So these would represent an entity as a function over all of its types using the same function regardless of the query. So the first of these would just be a simple averaging over the observations. And the second would be a max pool, which again is taking the maximum value at each dimension over the observations. And the second class of functions that we looked at were query-dependent. And the way we aggregate the observed types is going to be different depending on what type of question we want to answer. So if we had a query like, is this person a board member of an organization? We'd first calculate some similarity score between a representation of the query and each of the observed types. In the simplest case, again, this could just be a dot product between the two vectors. And in our max column method, the prediction would be made solely by the most similar observed type. So here, founder would be predictive evidence that Melinda is a board member. And the second query-dependent method we looked at was an attention-based one, where we're going to take a weighted average over all of the observed types, but relative to their similarity score to the query. So we can look at some examples from our entity typing experiments. So on the left is a query, and on the right is a set of observed types. And bolded is the maximum scoring type. So we'll see things like architectural engineer being predicted with the text mention engineer, baseball player predicted by baseman, and board member being predicted by organizational founder. Right, so these results here are based on our entity typing experiment. So this is similar to what we talked about before, where here the goal is to assign the correct set of types to each of the entities. So the first thing that we see is that the query-dependent methods perform much better than the query-independent ones. And this makes some sense because the model is able to focus in only on the relevant information for answering the question rather than having to look at a single abstract summary. And we also see that these methods actually slightly outperform the original model, which learns a single vector for each of the entities, even though it has far fewer parameters. And we can also apply these same methods to relation prediction. So similarly, the goal here is to assign the set of relationships that can occur between a pair of entities. So we again see a similar result trend where the query-dependent methods outperform the query-independent ones, and the query-dependent methods performing on par with the entity model. And the results here are a bit more modest than the entity type experiment before, and this is partially due to the data set itself, where a large number of these entity pairs actually only have a single relationship between them. So for those examples, all of these type-based methods basically reduce to the same model. So one nice property of this model is that we can combine it with our neural column encoder we talked about earlier, and that will allow us to make predictions about entities that we never saw at training time. So just as before, we can take a new sentence at test time and get a column vector with our encoder. And in the original model, we'd be stuck because, again, we don't have an entity pair row vector. But by replacing the explicit row embeddings with this aggregation function operating over the observed column mentions, now we can make new predictions about this encountered pair of entities. So we also evaluated how well can we actually do that. And we see that our type-based methods are able to perform similarly to how they perform for the entities that they did see at training time. And particularly, the query-dependent methods lose very little accuracy for unseen entities.
So when you say that those entities are not in the original data and you use the aggregation function, how did you aggregate the sentence then? Like if you had no embedding for them, then how did that aggregation work out?
So as
and Jane were not in the corpus at all,
right,
right?
but all of the columns were observed. So we do have both vector representations for columns as well as this encoder that it can encode new text that we see at test time. So the case here would be like Joe and Jane wasn't in the training corpus, but then they're in the test corpus, and we have some text mentions that represent them or that they occurred in. Okay. So another aspect of how we can represent knowledge in context is by expanding the amount of information that we can consider when we're trying to reason over a piece of text. So going back to our original document, in reality, the first step for almost any NLP pipeline is to do sentence segmentation. So we're going to split the text into different sentences. And after that, just as before, we're going to find mentions of entities. But some sentences are actually going to contain more than two entities. And the way we normally do something like relation extraction is actually we're going to consider each pair of mentions individually. So we'd have a Bill Microsoft example, Bill Seattle, and Microsoft Seattle. And the more mentions that occur in a sentence, the more individual examples that we're going to break that sentence up into. So this is a bit sad from an efficiency standpoint since we're re-encoding the same text over and over. But it also reduces the model's ability to jointly reason over the full set of entities at the same time. And the problem gets even worse in domains like biomedicine. So if we do the same procedure here, first doing sentence segmentation, in many cases this isn't an issue, and we're going to find some nice, concise relations. So this is in the title there, there's a relationship. But in other cases, we completely lose the ability to even attempt to make a prediction about these relationships. So for example, there exists a relation between this blue chemical, this red disease, but because they never co-occur in the same sentence, our model isn't even going to be able to make a prediction about them. And this cross-sentence relation phenomenon is actually quite common in domains like bio. So instead, we want to develop a method that simply takes in the entire text context at once and then simultaneously produces the graph of all entity relationships within the document. Okay. So the initial input to this model is going to be the full text of the paper title and abstract. And we're first going to map these to context-independent word embeddings. And in this case, our neural encoder will be this transformer from Vaswani et al., which is very good at encoding these large contexts efficiently. But the transformer inevitably is going to be a function that takes in our K tokens and contextually encodes them, giving us K outputs. And now that we have these contextually encoded our entire sequence, the next thing we want to do is predict the entity mentions themselves. So here we're going to find chemicals and diseases that occur in this document. We can then project each mention to two different representations, a head and tail representation. And this is whether they will serve as the first or second slot in the asymmetric relationships we want to predict. We can then get mention level scores as some function over that pair of representations there. So in this case, we're going to use a bilinear function. And we can do this process for each of our n relation types that we want to predict. And the only difference is that each relation type will have its own parameters, which is the pink matrix in this figure. And in many cases, we're going to have multiple mention level scores that are actually referring to the same entities. So just as we did before, we can aggregate these mention level scores together and give ourselves an entity level score, which we can use to make our final prediction. And this is important because in this particular type of data, we only have this entity level supervision rather than mention level supervision. So we evaluated our model on the BioCreative 5 chemical disease relation benchmark, and our brand model was able to outperform the previous state-of-the-art methods, which were ensembles of both feature and neural models. And we additionally ran experiments adding in a large amount of weakly labeled data, and as we had hoped, this is able to give us a pretty substantial boost in performance. So the source of that data was this database here, the Chemical Toxicology database. So this is a knowledge base containing genes, diseases, and chemicals. And the form of that data looks something like this, where a human expert annotator identified a relationship, which, for example, is between this chemical and this disease, and they also identify the article which they found the evidence for that relationship in. So from that, we can go out, find all of these articles that were referred to in the annotations, and then we can train our models to take in that abstract and title and produce the graph of annotated interactions. And we can do this procedure for the entire CTD data set, and we're able to produce a very large data set for us to be able to train our models with. And if you're interested in more details of the data set, you can look at this paper, but the main take-home message is that it is much bigger than the original CDR data set and allows us to train more accurate models considering a wider variety of entity and relation types. So if we look back at this model we just talked about, we can notice that we didn't talk about one component. And that is, how do we know which specific entities these mentions are referring to? So in our experiments, we assume that we know the particular entity linking decisions. In our experiments, we got these from some external entity linking model. And from there, we just had to decide, do these relation edges exist or not? But in reality, these mentions can be ambiguous, so that we don't actually know which specific entity these specific mentions are referring to. And what's worse is that in many situations, we don't actually have adequate amount of labeled data to train a supervised linking model. So just concretely, this would be like this. For this particular mention of this disease, it can actually be referring to any of these three disease entities. And this would be like if the text said Washington, you don't know if it's the state, the president, the school, etc. So the way that we're approaching this is to actually consider all of the possibilities together and think about the fully connected graph minus various constraints for pruning edges. So say we want to get the probability of the existence of this particular edge here. So we can actually decompose this a bit into three separate pieces. So what is the probability that a mention actually links to this entity? What's the probability that any mention links to this other entity? And then what's the probability that the text is actually expressing a relationship between these entities? And the important thing here is that we can train this model without any mention level entity linking supervision. All we need to know is that some relations must be true. And then we can even sample other relationships and say that they must be false. In addition to being able to train this entity linking model without mention level supervision, which is nice, we also now have a framework for a single model to perform all of the 8KBC pipeline that we talked about. So this would be mention detection, entity linking, and relation extraction. So the last thing I want to talk about is some future directions about how we can take some of these ideas we've talked about even further. And again, I think the main theme of this future work is how we can better represent knowledge in context. So a place that we can look for inspiration on how to approach this by looking at what we know about human memory. So one may be inclined to think of all of our memories as a single collection made of kind of the single collection made of the same underlying stuff. But in reality, humans actually have multiple interacting memory systems encoding different types of information at different levels of abstraction. So the starkest distinction is probably between explicit and implicit memories, where implicit memories are largely procedural or reflexive in nature. So this includes skills like tying your shoes or riding your bike, and these are things that you don't really need to think about for them to happen. On the other hand, explicit memories are encoding facts and events, such as how you know the capital of Massachusetts, or how you can remember a particular vacation you were on. And the main reason we know about this particular distinction is because of this guy, Henry Molaison. So he had these debilitating seizures, so doctors decided to remove a chunk of his brain. And while this did fix his seizures, after that he wasn't able to form new memories. However, they ran a lot of experiments. One interesting experiment was they had him sketch an outline of a shape in a mirror. They had him sketch the outline of a shape in a mirror, so all of his actions were reversed. So this is both a hard task and something he definitely didn't know before his brain was chopped out. So even though every day he wouldn't remember the task or the fact that he had done it the day before and the day before that, he would get better and better over time. And this was the first most important evidence of humans having multiple memory systems. And because of that experiment and future work, we learned that these memory systems are actually mediated by different brain regions. So without a hippocampus, HM's explicit memories were terribly damaged, but his implicit memories were intact. And from the perspective of the type of knowledge representation that we've been talking about, kind of a more interesting distinction is between two different types of explicit memory. So this would be semantic memories and episodic memories. So semantic memories encode abstract world knowledge and facts, such as a dog being a mammal, which is an animal. And importantly, these memories are not directly tied to individual experience. They're abstracted away and generalized. On the other hand, episodic memories are individual experiences within the rich context they occurred in. So this would be something like your interactions with a specific dog. And while semantic memories have facts like dogs being fast runners, your episodic memories would contain specific times you saw dogs running fast, as well as times you saw dogs not running fast. So the main idea I'm trying to get at is not that we need to make our knowledge representations strictly biologically plausible, but rather as we work to improve our methods, we can consider and take inspiration from a system we know is very good at knowledge representation and reasoning. So from the standpoint we've been discussing so far, we can really quite easily map semantic memories are really analogous with current knowledge bases. So encoding abstract facts without any particular grounding in a specific instance. And from here we can think about how can we leverage the idea of something like a rich contextual episodic memory for helping us represent knowledge in context. In a way, this can really be the text itself, where knowledge is grounded in these specific instances of information within a particular continuous discourse, including the full range of the surrounding context. So what might this actually look like? So one idea is we could imagine for each piece of text, we extract some representation over the sentences, encoded using some semantic framework, for example, like semantic role labeling or abstract meaning representations. We could then build these up hierarchically, connecting sentences into paragraphs, connecting paragraphs into full documents. And we can do this same procedure for many documents and continue connecting these pieces up to the level of the corpus itself. And as we build this hierarchy, what we're really doing is constructing a continuum of abstraction where specific concrete instances lie at the bottom and abstract knowledge at the top. And something like this would give us not only the type of abstract knowledge that we currently encode in knowledge bases, but now it could be grounded in specific events, each encoded within the rich context that it was originally observed in. And another type of context that is missing from current knowledge representation modeling is the concept of time. So nearly all research in this area focuses on knowledge and data from a single time slice, neglecting the fact that new information is constantly being produced and knowledge is constantly evolving. So this is another area where our understanding of human memory could possibly inform methods for integrating this type of information. So an important aspect of episodic memories is that they're inherently organized in a consistent timeline, which you can confirm for yourself as you very easily know the events of your lives and how they relate temporally to each other. So can we design models and representations that also have some intrinsic property of time built into the representations themselves? Because ultimately we want models that not only evolve over time as knowledge evolves, but that can reason about the temporal nature of events. So what we'd like is as new information comes in, we can add that new knowledge to our memory systems. And this includes not only adding knowledge, but updating our beliefs in the face of new information, which is a property common in domains like science. As new experimental results come in, we have to update what we know to be true. In addition to science papers, the same type of information stream can be seen in domains like news and Twitter. And I think the same types of principles could be beneficial in those domains as well. And what we've described so far, knowledge is really one-directional. As new information comes in, we can add it to our store of existing knowledge. But what we really want is to use the knowledge to interpret the new information itself. So this is another thing that humans do. So when we encounter some new information, relevant memories are going to be retrieved from long-term storage. And this prior background knowledge is going to be used to actually decide what this new information means, how it relates to all of our other knowledge that we possess. In some ways, we can again think of this as expanding the context for which we use to interpret information. That is, we look not just at the information itself, but also our complete understanding of how it relates to all of our past knowledge that we've already acquired. And lastly, I think we can imagine how this would be not just a single-step procedure, but instead how we can have some sort of short-term working memory where we iteratively retrieve, integrate, and reason over various concepts and memories. And I think this type of reasoning over existing knowledge is going to be crucial for advancing these methods, including the types of reading applications that we've talked about, but also things like dialogue, where there's a dynamic, evolving discourse being built up iteratively over time. Right, so just to summarize, I talked about methods for knowledge representation with the goal of being able to better acquire new knowledge and reason over it. We then talked about how we can represent knowledge in context, including a few first steps in this direction. And finally, how we can take these ideas even further in the future, the potential for taking inspiration from cognitive models of human memory. So before I wrap up, I just want to thank my various great collaborators on these particular projects I presented. And that's it. And thanks, and happy to take any questions.